along the course, we are going to design a very simple processor. During this first week, we will introduce the concept of processor and will give a partial specification of our particular processor. First, let us go back to the examples of digital systems described during lesson 1 of this week. The first one was a temperature controller executing this algorithm. The second example was a chronometer executing this other algorithm. We have seen in lesson 1 that to each of those algorithms can be associated a digital system. To the temperature controller corresponds this system, and to the chronometer this other system. Now, as regards the way those systems will be designed and implemented, there are several options, among which the designer will choose the best one in function of parameters such as the cost, the accuracy, the size of the final system, and so on. A first option is to associate to each algorithm a completely new system that executes the corresponding algorithm but could not execute any other algorithm. The way this first option can be considered is, up to a certain point, the main topic of this course. Nevertheless, both algorithms have some common characteristics. A first common characteristic is that both algorithms are made up of instructions that are sequentially executed. For example, in the case of the temperature controller, the instruction executed at time n could be this one. If temperature is smaller than the position minus half a degree, then the output on-off must be equal to on. If it is greater, then on-off must be equal to off. This could be a first instruction executed at time n. At time n plus 1, according to this algorithm, the executed instruction will be wait for 10 seconds. Then the next one, according to the loop construct of this algorithm, the next one will be the same as the instruction executed at time n. At time n plus 3, once again wait for 10 seconds, and so on. So this is a first common characteristic. Both algorithms, all algorithms in general, are made up of sequentially executed instructions. A second common characteristic is that sometimes there are branches and jumps. For example, in this instruction of the first algorithm, this one, there is a branch. If temp is less than position, then on-off will be equal to on, while if temperature is greater than position, then on-off will be equal to off. Another example is the while loop here of the second algorithm. The corresponding instruction is executed only if condition stop equal to off is true. Now, a third common characteristic is that both algorithms include instructions that read input values or generate output values. Here are some examples. In the first algorithm, in order to execute the first instruction, it is necessary to read the current value of temperature and the current value of position. Once a decision has been taken, the value on or off must be transmitted to the on-off output. In the second example, in order to execute the while instruction, it is necessary to read the value of the stop input. Another example here, once the new value of time has been computed, it must be transmitted to the time output. Finally, last but not least, some instructions execute computations. In the first algorithm, the computation of the difference between temp and position must be computed in order to take a decision. In the second algorithm, the updating of time includes, for example, an addition. Then, a conclusion. The fact that many digital systems can be defined by algorithms with some common characteristics suggests another way to implement them. Instead of designing and implementing a new specific circuit for any new system that we want to implement, we could first design a generic system. A generic system that includes input and output ports in order to read external data or to transmit external data to the outputs. It includes memory elements, for example, x0, x1, x2, and so on, able to store data necessary to execute the algorithm. And it must include processing resources or computing resources able to execute computations such as arithmetic operations and so on. Furthermore, this generic system must be able to interpret instructions such as write within memory element xi a constant value a, or transmit to the internal memory element xi the value of input port j. Here are the input ports. On the contrary, transmit to output port, one of these ones, the value of an internally stored variable, or transmit to an output port a constant value a, execute an arithmetic or a logic, some function, some available function f, using the value of some internal data and updating the value of an internal data xi. Function f is assumed to be one of the processing resources of our generic system. And also, it must be able to make jumps and branches such as go to instruction number n, or go to instruction number n if some condition holds true, so that it received external instruction. We will read later on where from come those instructions, and also it generates some conditions such as xi is equal to some constant value, or xi is greater than xj, and so on. Summary of this lesson. Another way to implement a digital system is to use a predefined generic system of this type. And this generic system will be called a processor. It receives input data through input ports. It transmits output data through these output ports. It stores internal data, x1, x2, x3, and so on, and it includes internal processing resources. This is our generic system. Then a list of instructions will be called a program, must be generated. It is the way a specific system is implemented by using this generic processor.